Hey folks, myself Kumara. I work for Microsoft and I started contributing to GRO while in VMware itself. Previously, I was part of VMware. So I have been, even after the switch, I have been contributing to GRO whenever I find some time. So as you all know, GRO is widely used software offload technique where multiple TCP segments from the, as soon as the packets are received at the network card, is subjected to this layer and to form a single large TCP segment. So this, by doing this, what we achieve is per packet processing like firewall, flow lookup, all those would be optimized in the network stack. So there are many TCP, the Linux kernel is also always with GRO on. There are many advantages to it. So in DPDK, there are two modes of GRO. One is the lightweight mode, where packets in a single burst are coalesced. The flows belonging to the packets belonging to the same flow are coalesced in a single burst. Heavyweight mode, where these are subjected to timer, where packets across different bursts are subjected to the GRO layer. So how, this is just a diagram from the DPDK documentation itself on how the existing GRO is actually doing the reassembly logic, where as soon as a packet is received, we check for a GRO table to see if this is an existing flow. If this is not on flow, we create a new flow and store the packet. If there is an existing flow for it, there is a logic to search for the neighbor and merge the packet to form a larger packet. If not found, we store the packet until we find a next packet or the timer expires. So the current implementation of GRO is a bit suboptimal. This is optimal for, let's say, packets in a single burst because packets in a single burst would have probability of belonging to the same flow. So what the current approach does is checks in the table iteratively to check if there is a flow match. So this flow match is based on the key of, let's say, 5 tuple. This is a basic TCP IPv4 without any VXLAN or anything. So so every time when there is a packet in the whenever the packet is received in the RTETH RX burst, this table is looked upon iteratively. So when we combine, as we increase the timeout, let's say from 1 millisecond up to, let's say, a few milliseconds, then the number of bursts would actually cause this particular function to be suboptimal. So the next obvious approach is to use a hash-based approach. So the hash key is derived based on the 5 tuple. So if RSS enabled, then the hash key can be reused from the RSS field itself. And if there is a collision, current approach is to use a linked list. So if the RSS is not enabled, then current implementation that I have done is just to do an XOR of all the tuples. So if the distribution on this is not really optimal, we could change this logic as well if required. So now the flow search is flow search logic is based on the hash table. So how was this validated is create IPF client and servers with TCP, test PMD in between. So what this test PMD's functionality is to just do a GRO and TSO in between. So since it is a VM deployed between the client and server, I had to really change the ARP entries in the client and server to, let's say, point to the test PMD's MAC addresses. And also the since there would be an IP address change, we will have to fix the checksum as well. So I used a BPF filter probably to change the MAC addresses and fix the checksum here. And there was a throughput that was run between the client and server. So the first numbers is, this is just a flame graph on, let's say, 32 flows with 32 connections from IPF client to server. So what we could see here is that with the current implementation, we see around 30% of the time utilized in the RT-GRO reassemble function, but with the hash based, it's close to around 18%. So this is a relative performance, relative consumption of RT-GRO reassemble function in the during the test that was run. So with 64 flows, we see that the current table-based iterative approach is taking around 33%, and the hash-based approach is taking around 15%. So also to measure the worst-case scenario where what is the cost of the hash itself compared to just the table lookup. With single flow, there isn't much of a performance difference. So it's close to 17%, both of them. And this is just the graph plotted across whatever numbers we saw. And can we integrate such test suite in whatever test DUT that we have? So, yeah. And also, this is the next part where today's GRO, irrespective, DPDK could host varying applications. Let's say it could be banking transactions, and it could be, let's say, backup and recovery server that is running. So any packets hitting from the application would now hit the GRO layer. So the applications, each of these applications could have varying latency tolerance. So banking transactions would require very minimal latency, but it is okay to actually have a latency in the other application. So, but having a single GRO timeout for the entire system is not really ideal, because let's say if the TCP connection across the two peers have window scaling sizable, then you could actually have a GRO larger timeout so that the packets would significantly decrease, subjecting the flow to a larger GRO timeout. But the other application, let's say whichever is latency sensitive, would suffer because of this larger timeout. So now, as you could see, there are different time intervals. So even though the packets from the application green could have been coalesced for some more time, could have a better GRO optimization, but because of the latency requirement of the other application, we had to set up a GRO timeout that is viable to both these applications. So we always choose a middle ground between on choosing the GRO timeout. So the proposal here is to, can we set a tuple specific timeout? The tuple could be anything. It could be, we could use the RTE flow and have masking on the RTE flow and put it in a separate hash table. So whenever there is a GRO flow created for a particular GRO entry created for a particular flow, we could refer to this flow table to see what is the specific timeout to be used. Applications could program the timeouts for the tuples. So this way we could the both low latency applications as well as for the applications wherever GRO would be beneficial for a, if we have a longer timeout, both could be utilized. So this is similar to whatever Linux TCP stack has in the egress direction, where there is a socket options where we can set the TCP no delay, which means packets are immediately sent out without being in the TCP socket layer. Or there is this TCP corking where we set, I think the auto corking today is around 200 milliseconds or something. So this is kind of similar to that, where we can implement this in the RTE flow itself for the GRO based solution. Yeah, that's all I have. Oh, sorry. There were few NIT fixes they had done previously. So initially, before this particular patch of reordering GRO packets, if you could say take a packet capture from, let's say a GRO, whenever there is a GRO subjected in the DPDK layer, you would see packets getting reordered. So this reordering was introduced in the GRO subsystem itself. So this is because whenever TCP in the GRO layer, if a TCP packet does not have a pure only ACK, then we deliver it to the application immediately. So even if we get a push flag along with that, we deliver the push separately, but there could have been GRO for the specific flow in the table itself, in the timer. But this is not the intended approach, because push means that we'll have to deliver the segment up to that point immediately. So this is how Linux GRO also works, where if there is a push, then the packets that are in the GRO table also have to be flushed together. So this patch was actually to fix this issue, and also added GRO support for IPv6.
So this you are doing at the end host or at a router or in middle. This is a node in the middle which is doing this GRO.
Correct. This is just for the test purpose, but in production scenarios, it could be, let's say, the past experience, we were using a load balancer.
Yeah.
So load balancer was proxying the connection. So
so then still it became an endpoint.
Correct.
Okay. And you were talking about this thing, right? That to have an options which are application specific timeout values.
Yeah.
So that maybe is definitely one option. And is there an option to detect that this is a short-lived flow or a long-lived flow, and do only for the long-lived ones, and the short-lived ones it doesn't matter?
Yeah, we could do that. So we will have to get some feedback from the application to say that.
No, because we're receiving the flow, right? So because we're receiving the flows. So from the flows itself, can we see that, okay, this is because it is short-lived, no need to do anything. If it crosses certain threshold, then only apply this.
Got it. But what my thought process is to have GRO layer as dumb as possible. So if you have, let's say, application specific, so these could be available with the application itself. Let's say, for example, if you are doing a proxy of a connection, right, at Nginx level, you know that get is, let's say, 1 MB or 10 MB. Or let's say
the application will also have to then determine, right? Because Nginx is, there are too many clients are connecting to it. So Nginx then will have to say if this connection is receiving so much packet, and then telling, okay, now you start doing the GRO.
But at least in Nginx, you know the response size upfront.
Yeah.
So with the response size, you can determine that, okay, is it going to be a short-lived flow or a long-lived flow? So
no, not really, because it's like if you're running a website, it's your right, you don't know, right,
correct.
What is it.
Yeah, that is true. Probably then we'll have to do some sampling at the GRO layer itself.
Exactly, right, and then see how it. Okay, fine. Thank you.
Please, could you explain your use case? Where are you using GRO today? And what is the performance benefit exactly?
GRO currently, with the current org, we have not been using GRO, but the previous, in VMware, we were using part of LB, load balancer.
Load balancer?
Yeah.
Okay.
So which was fully proxying the connection from front end to the back end.
Okay.
So while at the both the places endpoints, we were doing GRO there.
Okay. Yeah. At this time, your hardware was not capable to do it.
No. So it is not really hardware solution. So the ALB as such was deployed in the VM form factor as well. It could be in Azure, AWS, VMware, whatever SKUs there. But what from the past experiences, LRO is not that reliable is what we had felt from the previous experience. The first, I think you are mentioning about the LRO, right? Which is from the NIC itself, actually. Yeah. So LRO had some shortcomings. I don't know why LRO is not really being used in many places. Actually, at least we were not using it because it was not reliable.
Okay. So I suppose there was a big performance benefit, but there is a cost to do GRO in software, but there
Correct.
is also a benefit.
But there was a benefit as well in terms of CPU utilization at the stack level. So if you run a full-fledged stack where you have where you proxy the connection and let's say SSL and things like those, so GRO would benefit those business logics there, BSD stack and let's say whatever application you try to run.
Okay, thank you. Any other question? Okay, thank you then.